Yeah. Hey folks, I am
I'm not the last one.
okay.
I'm gonna take all the heat off you.
All right. I am Henry Strickland, and I've been working on projects using the Raspberry Pi Pico and the microcontroller that those are based on, the RP2040 and the RP2350, and applying them in our world of Radio Shack color computers and the Motorola 6809. And down at the last line on this page, you can see I'm crediting Thomas Shanks here for kind of beginning this project, or really beginning the most general aspect of let's build a board that's very flexible, that we can experiment with all that this chip can do. And he did that 2.5 years ago or so, and we had it ready at the Vintage Computer Festival in Orange County in 2024 in February. So that's how long we've been doing this, is really just 2.5 years. And the reason for the snarky title, RP2350 walks into a 6809 bar, is we may or may not be welcome here. If you're into old vintage retro computing, you can ask, what are you doing with this modern microcontroller in your computer here? Shouldn't you, have this the CMOS cookbook and the TTL cookbook out instead? But we do see modern stuff creeping in all over the place, and you look at like the mini MPI that we use, you look at the CoCoFEST, those have all got modern microcontrollers that we take advantage of, and we don't really think twice about, because we appreciate how much it helps us do what we want to do.
Without replacing belts on floppy drives.
Without replacing belts on floppy drives. That's right. Okay. The RP2040 is fairly new on the scene of microcontrollers, came out in 2021. And now these two newer models, and the RP2350B in particular is the one I'm talking about today, gets vastly better for what we're doing, because it now has 46 general purpose I/O pins instead of just 26, and I'll talk a bit about this. It's also 5-volt tolerant, which means that some of these extra glue chips that I used to use for buffering and level conversion, we don't need anymore. And in addition to Thomas Phoenix Brown, Rachel Koslinski, who's here, has been helping out with this. And so here's our history. I called it the Copicos, the one that Thomas made. The Aardvark was my version, because I had this idea that we could boot by something I called spoon feeding, which instead of having a boot ROM, we tricked the processor into executing instructions right after reset that we inject onto the data bus using SLENB, the SLENB line. And that actually worked, and that was really cool. Last year at this conference, I had the Bonobo, which did two things. It could succeed at spoon feeding, and it had a control port and a data port decoded in extra hardware. I didn't bring one, but it would look like little chips like this, extra hardware, but it would have the edge card on it. And that's because with only 26 GPIO lines, I didn't have enough to put the address bus to it. And a ROM needs an address bus to select within it. And so that's why it was spoon feeding and already had that one port decoded. But this is a game changer. Now, this year we've got the Centipede, and I'm going to say it can do anything and everything. And This is version 32Z. This is the one that got available at this conference and should be able to support into the future. It's not perfect. I ran into problems with the board before this and the board before this were not reliable, but the version 3 before this were. So getting frustrated with these other two boards, I went back to the one that worked, and it had 4 bodge wires on it. And I just took it, plus the 4 wires are now built in instead of bodging, and I called it Z instead of versions D, E, and F, the way I was progressing. So we may do a better job than this at some point of laying things out, but that's where we are now. So, anything and everything? What can we fake with this general purpose microcontroller? Today I'm demonstrating down in the room, and I posted to YouTube a couple weeks ago about it, these 4 things. It acts as a cartridge ROM. It acts as extra RAM for a CoCo 2 that only has 16K, but we make it 64K. It acts as a floppy drive, and it's exporting a copy of every write cycle done by our 6809 CPU in our CoCo off to a Raspberry Pi Pico or some other PC that can use that data in order to have its own idea of our memory image, and it knows what video mode we're in and can display crisp video. And one reason that's actually important is because when you do this funny expansion on a machine that only has 16K and it acts like it has 64K, you're doing writes above the 16K section, and those are getting aliased down into the 16K of real physical memory that your VDG is displaying, and that causes weird artifacts on your VDG display. And so here with this final feature, we are correcting the problem that we made earlier. And in this talk, we should be thinking about more stuff we can do with it, like making 128K or 512K and a memory mapping unit, the style that was in a CoCo 3, apply that to a CoCo 2. This is what the wonderful Mu card by Torvald in Switzerland did. He's not making those anymore, but I think we can do it with this. CoCoSTC, if I can emulate a floppy, I just have to do some more protocols and I can emulate the CoCoSTC, or at least the easier parts to figure out. Orchestra 90, as I understand it, that's just 2 latches, 2 8-bit latches, and probably, I don't know how they did it, but probably a resistor ladder, a digital to analog converter. How would we do that? We would use a pulse width modulation output because we don't have an analog output, but we can get really close with that. I'm really excited to try VGA output. The Bonobo already did Ethernet, internet kinds of things. We could probably emulate the WizNet API.
Yeah, basically the problem is the Pico board's Wi-Fi is super weak and low end. Like it's $1 chip they've thrown on there, and it's so bad that it's unusable basically. So we have to do something different to make it usable, especially in an environment like this.
Yeah, what Thomas is pointing out is that we did 2 years ago play around with the Wi-Fi and we got frustrated.
Off-the-shelf
Pointing fingers and blaming, I don't know. I don't feel that I'm confident we did everything the right way, but Wi-Fi is kind of hard anyway, and getting past gateways and stuff, and as long as these cards are tethered to a PC, that PC is a lot better at getting on your hotel's Wi-Fi or Starbucks Wi-Fi or wherever you are. So we've kind of punted that problem, and we're not trying to use the W version of these anymore.
Not this year.
Yeah. However, FujiNet does do Wi-Fi, and I designed a socket there, a 20-pin socket that can fit into a hat like this. And now we've got the FujiNet's hardware, which is a ESP32 that does have Wi-Fi on it, and they've got solutions to these problems. I also put a micro SD card on there, like the FujiNet people do. So we've got maybe an alternate implementation of what they're working on, and William Athing here is familiar with this, and we've been talking about sharing our experience in code and seeing if we can get this to work. DriveWire is always appreciated by people. There's a whole lot you can do if you've got I2C or SPI interfaces. And again, we've got the ability to add devices. And I have a generic version of the hat that you can put the pins in and put whatever device you want on there. You want to record the temperature, motion sensors, all the, you can get kits for $20 off of Amazon with all kinds of sensors to play with. And we can write device drivers for OS 9 that would let you get at it. And last year I had a real-time gaming OS that I had worked on, and I want to get that converted to use the Centipede as well. So at this point it says I'm supposed to go sub my images folder. So if you're on the GitHub, these images are there as well. And here we go. So I'm drawing a picture of a CoCo with a 6809 in it, of a CoPico card plugging into the bus there with the Raspberry Pi Pico processor, one of them, depending on which board you've got. And then a USB cable going to a PC. When I say PC, I use Linux on Intel most of the time. At this show, I'm using Linux on a Raspberry Pi, but I've also can compile binaries of this Tether program. I call it Tether because it's tethered on the USB for Windows and for Mac, either older or newer Macs. And that can give you access to a screen, to a keyboard, to disks, to the internet. And that's kind of the architectural picture that I live in. But notice we have to have code on the 6809 that knows how to talk to this. We have to have firmware on here, and optionally we've got a server running on a PC that's connected to it. And I'm going to mention just once that I've also got a single board computer which has a 6309, the Hitachi chip, and a Raspberry Pi Pico. And this I've called the TFR9 architecture. And I had these last year and talked about them. And there's more available if you want just a little thing to run OS 9 on and play with, or if we would like to get it emulating a CoCo. I'd like to get it emulating a Phoenix. That's a fun thing to play with. Oh, and I've got a demo where there's 8 of these running as a compute cluster. Actually 7, because I stole this one for for showing you here. And it's the same kind of picture, except it's going directly to the 6809 instead of going through the CoCo connector, which is a little bit different. So if we're going to fake like we're a peripheral, we kind of have to understand a machine cycle on the 6809. And the 6809 has 2 clocks. One is called E and one is called Q. Q stands for quadrature, which means that it's 90 degrees out of phase with E. And So a machine cycle is defined from the drop of E until the drop of E on the next cycle around. And Q is going to go high somewhere in the middle of it. And there's read cycles and there's write cycles. Actually, you could say there's non-valid cycles as well, but on a CoCo, we don't have the lines that tell us that. So we just think they're all read cycles or write cycles. And there's a specific period of time from the fall of E until the 6809 is going to be putting out a valid address and a valid signal of whether you're reading or writing. If you ever hear somebody say it's before Q or after Q or something like that, they're not looking at the correct charts from... Oh, and I should have put an E up here at the very top, 6809E. It's a little different for the E than it is for the 9E, and we have an E. But anyway, it's based on the fall of E there, and the reason why is because on the 6809E, the CPU does not control E and Q. It doesn't know when we're going to send the Q, and so the timing can differ. And now let's zoom into those cycles which are write cycles, meaning the 6809 is writing to RAM or to a peripheral. Now Q comes into play. After the rise of Q, there's a specified amount of time until the 6809 will be putting correct data on the data bus. And the general principle is you give it plenty of time to set up, and on the fall of E is when the RAM or the peripheral actually consumes that value. And then the 6809 is going to turn it off a few nanoseconds after the fall of E again. And a read cycle looks like this. We discover after this amount of time that the read-write line has not fallen, saying it's a write, so we know it's a read cycle. And we're free to do whatever we want during this time until here. Some of the time before the fall of E, or the end of the cycle, is called the setup time. We've got to have the data valid on the bus in order to set up. And when you want to know what these are, you go to this chart, and it's got the timings in circles, and it tells you the minimum and the maximum depending on which version of the 6809E you're using, the faster ones or the slower ones. So always go to this. That's the first rule. The second rule is take it with a grain of salt, because this chart does not know what the resistance or the effective capacitance of the lines are going from here to there, and that can slow it down. In fact, it can not only slow it down, it can add jitter that makes it look like E is bouncing or Q is bouncing. And I had that problem, and I solved it by cleaning my E and my Q with a trigger on this board. That's what this one extra glue chip is it has a hysteresis so that the switching high and the switching low level voltages are different, and that got rid of jitter and made it actually work. Okay, I'm supposed to be in my images still. So I'm now pretty comfortable with the 6809E and how many lines it has. There's 2 clocks, there's 16 address lines, there's 8 data bus lines. There are 6 lines that I call signals, which are coming out of the 6809, telling you what status, or the column status. The only one we really care about is read-write. These others we don't even get on a CoCo. But if you do get them, it makes it easier. Like last instruction cycle tells you that the next instruction cycle is going to be the beginning of an instruction, the fetch. That helps you decode what opcode it's doing. There's 5 of these that I call the commands that are going back into the chip: reset, halt, non-maskable interrupt, fast interrupt, and then I always ignore the 3-state control and just keep it at ground, and I'm not going to talk about it. But let's see, that's a 40-pin thing, 2 clocks, 16 addresses is 18, 8 is 26 with the data, 6 more is 32, and 1, 2, 3, 4, 5 more is 37, and that leaves 3-state control plus 5 volts and ground. That makes 40, so that checks. However, when you're plugged into a CoCo, you have to use this expansion port, and it's got lines that are a little bit different. There's still 8 data bus and 16 address bus, but CoCo makes up these 5. The cartridge signal, the secondary cartridge signal, the cartridge reply, let's call it, this wonderful line called SLNB, that when you assert it, all of the I/O devices and RAM and stuff inside the CoCo back off and let you take over the data bus. That lets us fake a lot of stuff. And they have a sound, which is a little complicated but gets routed around. The normal lines, they give us non-maskable interrupt and reset and halt. They do not give us directly interrupt or fast interrupt, although fast interrupt is often tied to cart. We get the read and write signals, the E and the Q clocks, plus 5 in ground, and then we're going to ignore these extra voltages that a CoCo 1 had. So let's see, that left 35 lines plus power levels. So potentially 35 signals we might want to route to our 46 lines on the GPIO. Now let's look at the RP2350. I've dedicated GPIO 0 through 7 to the CoCo's data bus, and at the bottom I've dedicated GPIOs 32 to 47 to the address bus. And which of these ranges on the left, 0 to 15, 16 to 31, 32 to 47, you kind of want to think about, because when you're using programmable I/O, the programmable I/O is built around the idea of a 32-bit machine, and it can only do 32 bits per PIO, programmable I/O block. And so a PIO block is assigned to either the top 2 or the bottom 2. But it also means that the things in the middle here are going to be available in every PIO block. But data bus is only available on some PIOs, and address bus is only available on other PIOs. So far, I have not used PIO in the things that I told you that the Centipede was doing previously, those 4 things we talked about. But we will be using some when we're doing things in the future. And GPIO 12 through 19, I want to keep free, because those are special high-speed transmit lines that can help you output video up to and including some basic level of HDMI. That's a little challenging. I'm going to start with VGA and try to output VGA using those lines. 10 and 11 are a good choice for the I2C. 8 and 9 I'm disappointed with. I have put CTS and SCS on them. I really wanted to keep them free, but at least on this Z version of the board, they're no longer available, which means you can't use 8 through 11 as SPI protocols. So like, it rules out having both SPI here and high-speed transmit here. You'd have to put your SPI in this area.
Those are hardware features of the RP microcontroller.
Right, hardware features of the microcontroller, and that's really what we're talking about here. So these are the things that you think about. It sucks that 23 and 24 are forbidden, and they're in the middle instead of being on the edge. 25 is traditionally used for an LED, and so I did the same thing. And I won't say anything more about this now, but this is a good thing to get a feel for and master when you're going to start to experiment with it. It's the kind of thing that we didn't know really well when we started 2.5 years ago, and is why we made our boards experimental. I'm checking the time. We've used almost half an hour. Should I stop for any questions at this point? Okay, I'll keep going. You are allowed to interrupt me, and I'm allowed to say I'll answer you later. But whatever, we'll work it out. Now I'm going to talk about 3 routines: foreground, background, and main. So when you compile for your firmware running inside the processor on this CoPico board, I'm writing in C++. One could also use Python to do stuff, and even though that's a lot slower, there's a lot you could still do with it, but very quickly I switched over to C++. You write a function named main, just like you usually do in C. It starts out, I initialize the pins, I make the mostly inputs, I make the LED output, and then I initialize other features of the microcontroller, such as the special USB port here. I get it initialized, and I initialize the standard I/O library to talk to it. So I can use getChar and putChar to talk to the USB to the tethered PC. Now, foreground and background. This is going to look kind of strange. Usually you think of starting a background task in the background, but I'm going to start the foreground task on CPU number 1. We're currently running on CPU number 0, which is going to do background. And foreground, the timing is very important. Background, it is not. That's my distinction between the two. And the reason to run background on this first processor, CPU 0, is because that's where the interrupts are. So I'm allowing background to be interrupted. I don't want foreground to be interrupted. There is a communication channel between foreground and background. So let's go back now to the foreground picture. It's an infinite loop that says, while the E clock is low, wait until E rises. That means we're halfway through the cycle, and by that point, the address bus and the signals like read-write are definitely available. Whether you're reading or writing is a bit, it's a function of the signals. And now we know if we're either reading and we do the top half, or if we're writing and we do the bottom half. In a read cycle, we know the address that the CPU wants to read, and we call a function or do some work to come up with the byte that we're going to hand back to it. Depends on whether we're a ROM or a RAM or a disk device or just how we're going to do that. And so I drew a big green line under it. It means we'll talk about this later. But we get a byte for the data bus, change the direction of GPIO pins 0 through 7, that's what we connected to the data bus, to be outputs from the PiPico, which will be inputs on the 6809. We put D on those pins, and then we wait for E to drop at the end of the cycle, and then we change the direction back. So that's a read cycle. A write cycle, we wait for Q to drop, and then we read the data bus. So we're already 3/4 of the way through the entire cycle when we get our data bus value, and then we do something with it, depending on what the address is and what we're trying to emulate. So another big green line. And this is a tight loop that is keeping up. And the reason it can actually keep up is, by default, we're running at 150 megahertz when your CoCo is running at 1 or 2 megahertz. So we're at 150 megahertz, but I actually overclock it to 250 megahertz. And on this board, 50 out of 50 overclocked that well and worked. But what if we need to do something like go over the USB tether to get a disk sector, something that's slower than the cycle here? There is a FIFO between the foreground and the background, and we can put a 32-bit word into that FIFO. And now I'm showing the background. What background does is it sits right here where it says get from FIFO blocking, and it's usually sitting right there blocked until it gets a request from the foreground. Now, we don't want everything in the foreground to be shoving something here, but sometimes it has to. And so that we don't get overloaded, don't overrun the FIFO with too much data at once, we activate the halt pin as soon as we get something, and we're going to halt the main CPU at the end of the current instruction until we're finished in the background. That gives us some time. We buy some time by telling the CPU to go into these idle cycles. So I activate the halt pin, and then I switch based on the upper bits of the request. Maybe the request is a put char, that we're putting a character on into the log on the PC, or a disk read or a disk write where the PC is going to give us stuff. And we can add lots of other cases. And then we loop back around, and we deactivate the halt, and we wait for the next thing to do. So that is how everything is architected between foreground and background. And now my images are done, and I do a return statement to this page and show a little bit of C++ code. In order to do I/O ports, I have an array of 256 readers and 256 writers. This using statement is the new way of doing type defs in C++. And so a reader is a function that takes an address and returns a byte. A writer is a function that takes an address and a byte and returns nothing. And so these 256 correspond to FF00, FF01, FF02, all that top page that's for I/O. And I'm also going to make an array named RAM and make it 128K big. And so I'm not using all of that yet, but I've reserved that space. There's this wonderful thing in C++ called the curiously recurring template pattern. I spoke about this in January on Mark Overhoser's virtual fest, but it's a way to kind of do the same thing that you would do with conditional compilation. You want to if-def something in, if-def something out, but really I want to have both versions available so that at runtime, without reflashing my board, I can choose the fast path or the slow path. I can skip the logging, or I can go turn it on again. And so I do that by having a templated class don't log and do log, where don't log does absolutely nothing right there, and do log does whatever it needs to do to get the message into the log on the PC. And so I can call t::log from lots of places, and you don't know at the time you're writing the code, but you do find out when it's being compiled and linked whether the logging is going to take place or not. And the optimizers, you can assume, completely erase things that don't have any effect. And here's another place to use the curiously recurring templated class. Do we have big RAM that needs a memory mapping unit, or do we have small RAM in which the addresses are not remapped? And I can do peeks and pokes to the big RAM or to the small RAM I'm talking about the version of the RAM that's within the within the PyPico. So here's how you combine these mix-ins into I call it an engine. So I'm going to define one fast engine and one slow engine. The fast engine doesn't do any logging and uses small RAM because there's no memory mapping. It'll run faster. The slow engine is going to do all the logs, and it's going to do big RAM at the cost of running a little slower in that part of the code, which might limit what all we can do with this. And now inside of main, we need a way, and I don't have a way yet, but someday we will, to decide we want to run the fast engine or we want to run the slow engine. But both get compiled and both are available. We talked about, in my pictures here, doing a read cycle. Let's see. Actually, we talked about it here. Here's the read cycle, was these 4 steps. Here's my actual genuine code. Starts with an if reading, and I'm telling it that likely we are reading, and it can optimize for that. And it actually saves you a few nanoseconds when you tell the branch prediction correctly what you're doing. If the address bus is in the I.O. page, meaning that as an unsigned int it's greater than FF00, we look up the reader R using the address bus's lower 8 bits. And if it's not null, we call that in order to get our data bus. We change the direction of the output and put it on the data bus. If it wasn't in the I.O. page, if we're turning a 16K CoCo into a 64K CoCo, then we peak that address off of the data bus, and that peak is either going to be the slow RAM or the fast RAM. It can be the slow RAM in this case, and we put it out. Otherwise, we don't get involved because maybe we're reading from some other device. And then we stall waiting for E to drop and change the direction to make sure that it's inputs. And yeah, here's where we set the direction to inputs. So that's my genuine code that I'm running down the hall in my demo. And this is the right version of it. It also has the ability to look for a writer if the bus is greater than 0. Yeah, if W, then we call that function. This I'm still using conditional compilation, the old style. This is if we want a record of every single write that goes on the CoCo. It pushes it with a magic number in the top few bits and the address and the data bus. And that's going to go to the background task, and the background task is going to send it down the USB to the tethered PC. There's a different set of code that's run if we are the disk cartridge or the ROM cartridge. And here's some of the cases for read, and here's some of the cases for write. And notice we have the floppy latch that tells us which floppy drive we're using. We can issue commands here which end up pushing a byte on the FIFO to the background to say do a floppy command. And the data reads and writes are on FF3B, and they end up incrementing a pointer that's pointing into a buffer that you read. And once you have read all 256, we tell it to tell the floppy to write that data and cause a non-maskable interrupt. If you're familiar with our floppy codes, that sounds familiar. And And how do we fake 64K RAM? I've got the code for that here as well. And I'm going to focus on the init. Notice we've done a don't version and a do version of this. And the don't version all has no ops as the or identity functions. The do version is going to install these 4 writers for setting and clearing the SAM bits. There's the SAM bit called P1, the SAM bit called TY, and TY tells you whether your RAM goes up to FF00 or it stops at 8000. The P1 bit tells you whether you want to swap the top and the bottom halves of RAM. This is built into every CoCo. This is done in the SAM. So I have to emulate it. And there's reasons for it. And another example is adding a UART. And the 6850 is pretty easy. It has one control status port. It has one data port. And we either don't or we do include it. Motorola called it the ACIA, the Asynchronous Communication Interface Adapter. Most of the world calls that a UART, a Universal Asynchronous Receiver Transmitter. And the install function installs a reader for control, a reader for data, a writer for control, and a writer for data. And that's like the end of my presentation. I can go into more details. We can talk about grand ideas. We can talk about how to emulate other things, how VGA has been done in the past. If anybody's got questions about stuff. Yeah, it would.
Using the ARM side or the RISC-V side?
I'm using the ARM side.
Okay, and then what about the SDK? Using Pico SDK or doing bare metal?
I'm using Pico SDK,
Okay.
and I'm not using RTOS.
Okay.
And trying it with the RISC side would be interesting, but I barely got here with a working card and enough versions. So.
The ARM side is a little bit more optimized at this point. The RISC-V is experimental.
Okay, William thinks the ARM size is more optimized at this point, and that makes sense. But I think it's great that they're encouraging us to go ahead and start to try out the RISC, which could be a hint that in the future they no longer have to pay the license fees for ARM, and they can make these even cheaper. And more open source. Yeah. Tommy, input?
I think some people may have spotted that you're halting the processor right now to get some I/O done. That's the kind of thing that using the PIO could probably eliminate, but it wasn't necessary to get the demos working. So
Yeah. So it's
functions working, and then we'll go back and optimize.
It's a little unfortunate that I'm halting the processor. I may not need to do that for what we're doing right now, but the time the FIFO from foreground to background would get overloaded right now is when an interrupt occurs and all your registers get stacked, and I'm keeping a record of every write that's going across the USB. So it's times like that that I'm pushing it the closest. But I've been doing other experiments where I try to log every single read and write, and so far those have always crashed. So halting the 6809 for a little bit was expedient in helping me to get here without too many problems. Yeah, it'd be nice to.
Yeah, you were doing the same thing when we were.
Be nice to take that out.
When you were first going to C code from the Python, also.
Oh, if you were doing it in Python, yeah, then you would definitely want to halt that CPU while you're doing stuff. Question?
I may have misunderstood what you were saying when you were talking about a floppy controller. It looked like you limited to 256 bytes. Is that?
That's typical. Okay, why is it 256 bytes instead of 512 for floppy sectors? That's typical for our CoCos, and
The copper protected stuff is it has 512 or 1024 bytes.
yeah, I believe the Western Digital 1773 floppy disk controller is capable of 256, 512, 1024, maybe even 128 bytes.
Yes.
And somebody at Radio Shack decided 256 is a nice power of 2. Meanwhile, someone at IBM decided let's use 512, and there wasn't a standard yet, you know.
There's a lot of the copper protected disks that are using.
A lot of copy protected disks are using 512, he says. Yeah, and I totally believe that. And so the read write track commands are available on the floppy disk controller. So a program could, by using the controller directly and bypassing the operating system, do exactly what it wants to on the floppy. And that was often done for copy protection.
Yes.
Okay, that makes sense, yeah. That's enough to stop me. It would keep me from running the program because right now I'm only doing 256 byte reads and writes. Very good, okay. What else is on your minds? Yes.
It sounds like you'll be backing up, well, you could just back up all of the logos memory onto the PC, the Mac, BIOS, have a virtual memory map. You
Yeah.
can debug anytime you want. It sounds like
Yeah, well, I mean, the attempt to log, I think you said the attempt to log all the reads was, in real time was not going perfectly, but certainly there would be a way to get that done. Yeah, absolutely.
Yeah, so as a debugging tool, it's nice to have a copy on your PC of what's in all of the RAM so that after everything crashes, you can go examine the dump. It's also nice to have a record of the read cycles as well so that you can see what opcodes are being executed. And I've got code to join such a dump with both reads and write cycles with the original assembly language source code so that you can see the names of the symbols and the comments as well. And one thing that would be pretty easy to do, and I've done versions of this, is have a watch point, like an address. Then on the nth time that this address did a read or a write, potentially of a certain value, that triggers the watch point, and you get a dump of the 1,000 cycles before and the 1,000 cycles after that watch point. Other people have asked about getting a single stepping debugging mode, and I have not tried that yet. I know that emulators are talking to GDB and things like that to do single stepping. I haven't gone that way because I found it useful enough to look at a trace of what did happen to debug and find my bugs. So like you're saying, that's a useful feature, and I need to find a way to package that better so that like on the tethering program's command line, you can specify not only do you want to keep logging on or off, but do you want a watch point at a certain address, and it tells the PyPico CPU to do that. Yeah. Am I hitting your points?
Or you could halt it and do a full memory dump. Yeah.
You can halt and do a full memory dump of the CoCo.
Yeah.
Yeah, that's right.
But the Pico is the memory at this point.
The Pico could have the memory or could not. It doesn't necessarily
Yeah,
have to
depends on
be
if you
that.
enable that mode, but
Yeah.
if you're doing the memory replacement, you're usually
Yeah.
answering.
So like a fine use of these would be to just insert it when you've got a thing you want to debug and you're not using anything else, but you're using it for debug. Another fine use would be to insert this and use it where it's not, it's only watching what's going on, but it's keeping a graphics buffer of things that you see and displaying graphics modes we don't have already.
Yeah.
It's kind of a passive thing. You don't ask it questions, but it watches and ends up giving you a
High-res graphics.
high-res display with sprites and tile maps and everything, and all of these things may not be possible at once, but a lot of it is.
I mean, you're doing 4 things at once.
Yeah,
That's
yeah,
not even using PIOs to help you with, you know, buffering.
yeah. And there's no way to determine what's possible at once except to try it, and then hope your conclusions applies to all other CoCos. Yeah, John.
Matches my philosophy of, you know, that, can I do this project or do this item? Well, to me, I prove I can't do it before I decide it can't be done.
So John has to prove that he can't do anything before he knows that it can't be done. And if you can't prove that you can't do it, you darn well better do it, right? Okay.
Thank you. Thank you for taking over my project and finishing it.
Okay. Tommy's had a very interesting year, and he really regrets not being down in the details. But I've been more fortunate with free time. Yeah, in the back again.
Is it possible to use this card with multi-pack?
Can you use this with the multi-pack? Sometimes. Some of the things that I've done, I've discovered, like for trying to log all the instructions, that they don't come through a multi-pack on a CoCo 3. And I have yet to figure out what all these limitations are. And that what it might drive me to do is make my version that has the RP2350B on it plug into your PC, into your CoCo, and then have a connector that your multi-pack plugs on into, so that I get first shot at everything going on the bus before the multi-pack decides I'm going to rebuffer and filter. So I'm thinking about that.
Yeah, you can base that on Ray's extender card. Yeah.
I was going to say a version of the mini multi-pack that has that built into it.
A version of the mini multi-pack that has this built in would be really neat, yes. And then once you've got this processor in there, do you need those processors in the mini multi-pack anymore? So look, this is all open source. I'm telling you all this and my experience so that you can all dive in and experiment and help. My code's on GitHub. I can help you interpret it. I've got KiCad models for every board that I've made up there. William is nodding. I think he's excited about these kinds of things as well. John?
I just want to verify he's been very open to listen to ideas and to sometimes implement them. So thank you.
So John has given me John Strong in the back here has given me some good advice at last year's CoCo that has influenced my directions and my priorities. And he says that I am actually open to listening to people. So thank you. And someone's scratching their nose. Okay. Phil. All right. Maybe this is enough. What time is it? Yeah, it's almost 4:30.
Thanks, Ray.
Okay.